I met you guys on the poster floor and heard a little bit about you, and I have to say what you guys are doing is really cool, and I'm surprised it hasn't been invented earlier.
I know.
There's a lot of people say that.
Yeah, some people have. They said some people may have been. I heard echoes that maybe people have tried something similar, but just nothing has ever come to a product that's sellable and that seems to work reliably enough, I guess.
So what is it exactly that you do? I don't know. Maybe some of our listeners don't know yet.
So, okay, I guess I should explain. So I'm from Actuated Medical, it's my company, and we kind of specialize in adding ultrasonic microvibration to medical devices and such. As kind of where we got our start for instance, for putting in epidural needles or spinal needles with less force so that the clinician can have more control. We also have a similar device for doing bone biopsies where you don't have to, grind in so hard, or sometimes we've heard of clinicians getting out a hammer to actually get into the bone. So we had met, actually our director of research, Roger Bagwell, had met Doug Weber at one of the DoD conferences a couple years back, and was telling him about some of the stuff that we do, and he's like, oh, could you use that to help get neural implants in? And so that's kind of where we began. I guess I should say, because I had a background in doing neural implants before coming to my current company, and we actually published a paper in 2011 or 12, I believe, I'm sorry, it was 2008, I think, I forgot, it was when I was still at Penn State, on using collagenase mixture to try to thin out the PIA membrane to better insert microwire arrays into rats. And in that IEEE paper, we were able to kind of show that on average about 40% force reduction. And we weren't quantifying dimpling then, but it would also, in some of the force profiles that we could see, that those peaks were happening earlier in the insertion, so presumably less dimpling. So once we kind of had this opportunity then to apply some of this vibration technology, I was really excited to kind of get back to doing neural implants. I'd been out of it for about 8 or 10 years or so. So we got started on adapting some of our technologies. We had to kind of work out how to couple to the arrays in a way that delivered enough energy or vibration to the probes without heating up or breaking things. And then, of course, when it took it all the way through to actually evaluating in a small animal study to at least demonstrate feasibility that these are safe for implant. The vibration doesn't kill the neurons, that doesn't produce too much heating, but it does have a great impact on the amount of dimpling, as you saw at the demo. So right now the system has been designed to work with Omnetics style probes with Omnetics, like a 16-channel Omnetics connector, although the could be adapted pretty easily, I think, to other technologies or other neural implants. But it's right now designed for probes that would be sort of in line with a connector, such as like a Tucker-Davis Technologies microwire array or microprobes. It also works with the CM style NeuroNexus probes as well. So, but it's
yeah, cool.
Yeah.
Very cool. So you were doing the test before, and you were able to reduce the force by 40%. Is that what you're seeing here as well?
Actually, no, it's even higher. With
wow.
Yeah, microvibration depends on the probes and how exactly.
Yeah, because I can think. I mean, I would guess that like lots of probes, spaced very closely together, it would be a big difference.
Yeah. It's we've seen as high as 90% force reduction.
Wow.
Yeah, but pretty regularly. It's at least 70% for most of the probes that we've tried.
That's incredible.
Yeah.
But yeah, the force, like you said, doesn't really matter so much as the dimpling.
It's more the dimpling, yeah.
Do you want to explain a little bit like what the dimpling means and like what kind of problems that can cause later?
So dimpling, what it means, it's sort of that pincushion effect. As you have more and more shanks or individual wires in the array, it will tend to be more difficult for them to puncture. They might puncture on the outside electrodes easier first. And people have tried different ways to deal with this. Some just go really slowly, like inch in like 100 microns at a time, wait, a minute, 5 minutes, and then do another slow increment. That's how I learned to do it in graduate school.
So it could take like a day or two?
Yeah, it could take a long time, a half hour or so. And surgery time is important to try to minimize as much as you can. If you do the other alternative is to kind of fire the array in like they do with a BlackRock inserter, which kind of out of necessity. That's what's done a lot in particularly the higher channel count 10 by 10 arrays and such they use in primates. I think in rodents they might be able to get away with a slower insertion somewhat, but so I guess it's not completely known. You can mention like what effects this has. There's been papers published though. The strain that you apply to the brain tissue stretches the microvasculature underneath, may stretch the neurons. There's been studies that suggest that can trauma of the insertion can impact immune response and recording performance of the array. I don't know if there's been good studies linking it to long-term performance, but one could kind of assume that if you can reduce that insertion, the strain on the brain and with the insertion, it should improve things. So I guess that's...
Yeah. Do you want to talk about how surgeons go beyond the point?
Yeah, so what often will happen is, let's say you want to target a certain depth of the cortex, and this is what we found in our rodent study. We were inserting our arrays at 50 micron per second, and if we would go, say our target depth in barrel cortex was 850 microns. If we went to that 850 microns, a lot of times the brain hasn't relaxed yet. We wouldn't see really a pop through, so it suggests that maybe the ray hadn't even penetrated the pia yet. So you kind of have a choice. Either you just wait there and kind of seal the brain up, seal up the craniotomy and hope the brain eventually pops through, and it may. Or you have to keep advancing, and what we did was kind of go 100 micron steps, kind of wait a little bit, 20 seconds or so, and then advance again if it still didn't look like the brain had relaxed. So sometimes we would see up to anywhere from, on average, is about 50% overshoot that we'd have to do. So
That doesn't sound like science. It sounds like art.
Yeah, it is. It's a bit of a, and animals, are different. You might have a part that when you did the door opening, maybe that the pia had been damaged a little bit, or it's just a little bit thinner, so it might not see that. But what we found with the microvibration active, that in none of those times do we have to insert beyond the target depth. So that could lead to, I guess, another benefit of reducing that dimpling, in addition to perhaps reducing the compression of the brain and what potential trauma that might cause, is to get more accurate placement. So you can, when you are done advancing, you can know you're at the depth that you want to be. And I could imagine in the future, maybe you could couple it with the recordings, which we haven't done a lot of testing with that, but we think the vibration works even if you've got you're connected to the electrodes to get recordings, and so you could envision moving down to a point maybe that target spot isn't giving you the best recordings. You have to be a little bit careful because sometimes people don't get the best recordings right at the implant anyway, just due to the trauma that's there involved in the surgery. But potentially in the future, you could know that when you're ready to seal up, that you've got your electrodes where you want and getting good recordings. So
so more of your more of your animals are, actually working, doing the thing that you want to do, and
exactly.
it's more reproducible.
Yeah, and a lot of time is, anyone that does chronic surgeries, a lot of time is invested in doing the surgery itself, and then, electrodes aren't cheap either, and so there's a lot put into each animal, and of course you want to minimize the use of the animals as well. So we're hoping that it'll be a tool that will help it, improve the quality of the data, and just get more reliable performance. There's always going to be surgical variability, and people getting better at skills and stuff too. But if we can try to kind of equalize or make the insertion process a little more uniform, then and getting best results there, maybe it'll help to get more repeatable results, and that you can compare across labs and such. So.
Yeah, that sounds good. Mm-hmm. Wow, very cool. So basically, it's going down, it's sending an ultrasound. It's vibrating the arrays at an ultrasound frequency, variable power is what you were saying as well. Mm-hmm. And this basically allows there to be less friction. I guess in physics 101, it's a difference between static friction and kinetic friction, right?
Yeah.
And therefore it slides much easier, and it also allows the cells and neurons and all this stuff to be able to adjust and
hence that's, I guess, why we got the name neural glider. But it kind of glides in to the implant. So or glides the implant into the brain.
Yeah. Very cool. Very cool. So what's next for your company?
Sure, we are. So the first system, and we're hoping to have it ready for sale. We're demonstrating it here. We've got a lot of excitement at the SFN for it, both at the poster that I presented on Saturday. A lot of people come by and saying, like, okay, I work with BlackRock arrays, for instance, or floating arrays. And right now, the system we'll be selling in January, as I mentioned, is more geared toward the fixed probes. But we have we have some grants submitted to help us fund the development of a solution for floating arrays as well, which we are confident we'll be able to accomplish that if we can get the resources to do so. And hopefully next SFN we'll be speaking on that.
You'll generate more excitement.
That's right.
Yes. Very cool. Very cool. Is there anything else that we didn't cover that you want to mention?
No, I can't think of too much. Just that we as a company, Actuated Medical, been around since 2006. This is kind of our first debut into neural implants and such, but we have a lot of hope to make some impact in the field, getting devices in.
Maybe making the least impact.
The least impact. That's right. That's very good. And then trying to maybe targeting peripheral nerves, spinal cord, and that sort of thing, and have thoughts for how to do this in a more a less invasive approach to that. So.
Okay. So what was Actuated Medical doing before? What is it they're still doing?
Yeah. So we have our first product out in the market is actually a device for eliminating clogs in feeding tubes. It's the Tube Clear device. So that's a 510K FDA market clearance, so it's been out there, and we're starting to get leverage into hospitals. We have a sales force out there working very hard to do that, and that's so that we can. Feeding tubes tend to clog when if they're not maintained properly, and the busy nursing schedules and stuff. Sometimes that just happens, and so the alternative is to kind of yank the tube out and put a new one back in, but that's uncomfortable to the patient, takes time and money, and you have to verify you're not in the lungs or somewhere else. But so what we provide with Tube Clear is with a disposable sump. It has a actuator at the back end to vibrate a wire. Essentially, it goes in and works on the clog, able to reverse it, and then you flush the tube while it's still in the patient, so they can get their nourishment again. So, and we have thoughts that it may have eventual application to sort of maintaining tubes as well, not just fixing a problem, but like you wash your silverware and such, after a meal. These patients that have the feeding tubes, they can have a more clean tube after they're done. And we also had one other product out there that I'm not sure if the video will make it or not, but the poking the banana that you had the interest in, the Gentle Sharp device. It's for doing less stressful, painful sticks for getting blood in animal models, and that's a product that's available. I believe it's sold on Braintree, but we think that kind of idea might work for some of these other applications, like the getting devices into the peripheral nerve and such, where it's a little bit tougher than it is for the brain. But so this kind of sums it up.
Yeah, very cool.
Yeah.
Very cool. Thank you so much.
Yeah, thank you very much.